afternoon session, and let's get started. Our first talk is from Anish Agarwal from UC Berkeley.
Hi, everyone. Thank you for attending. And firstly, I'd just like to thank the organizers for inviting me and also the Simons Institute for giving me a wonderful fellowship for this semester. So the title of my talk is Causal Inference for Social and Engineering Systems. So before I go into the specifics, I just want to give you a broad idea of the type of things I think about. So my work is really about bridging two fields, causal inference and econometrics, which thinks very carefully about how do you do causal reasoning despite unmeasured confounding, and connecting that the variety of interesting frameworks that have come out of it. For example, instrumental variables, regression discontinuities, difference and differences. In general, they're trying to find and analyze natural experiments that are happening around us. But in general, the estimators that come out of econometrics are designed for small economic data sets. So that's changing. And trying to bridge that with machine learning. It thinks about prediction with modern data sets. Data sets that are high dimensional, noisy, sparse. A variety of interesting frameworks such as kernel methods, neural networks, high dimensional regression have come out to deal with that. But they generally are not designed to handle confounding. Right? And so my aim is to bridge these two fields so we can get the best of both worlds. Specifically, my thesis has been about bridging two subfields. One is called synthetic controls, which asks the question of what if an intervention didn't occur? It's a core idea in econometrics. And try to bridge that with matrix and tensor completion, which is the core idea in EE, CS, stats, and ML. It's about imputing missing data in a matrix or a tensor. My thesis is about two pieces of the work. The first is synthetic interventions, which brings ideas from tensor completion to synthetic controls. The joint work with Shah, was my advisor at MIT, and Anish Shen, who's a longtime collaborator and a postdoc here with Bin and Peng and Jas. Don't think I see him in the audience. And the second piece of work is causal matrix completion, which brings ideas from synthetic controls to matrix completion. Today, I'm just going to talk about the first piece of work called synthetic interventions. So the motivating application for the remaining of this talk is going to be some work we did with an Alzheimer's Therapeutics company. Okay, so they gave us access to their phase 3 clinical trial data. There were 1,162 patients in that trial. They're testing the efficacy of 3 different therapies, plus placebo. So let's call it 4 therapies. And what they're measuring is something called the ADAS-COG score, which is the Alzheimer's Disease Assessment Scale, cognitive subscale, right? And that's a measure of cognitive ability. And the change in that is what the FDA cares about when they try to change, when they decide to approve or disapprove a drug. Okay, and this study ran for 2 years. And so the reason we worked with them is that at the end of the 2 years, they actually found that the average treatment effect of all 3 therapies was insignificant. Right? And this is a big problem for them. The cost of the trial that they ran was more than $500 million. The cost of recruiting just one patient ranged anywhere between 5K to 100K USD. And not to mention the ethical concerns of testing on human subjects. So the question we set out to answer with them was that maybe there was a subpopulation for which the therapies were effective. So towards that, we wanted to ask a relatively ambitious question, which is that can we estimate the ADAS-COG score for each patient under each therapy? Okay. This is the question. I'm going to show you how you can pose this question. Just simply pose this question as one of tensor completion. Okay. So key object of study in causal inference is potential outcomes. So in our setting, potential outcomes will be indexed by N, T, and D. So Y and TD refers to what if patient N on visit T had been assigned therapy D. One way of thinking about this, at least visually, is through a tensor. Okay. So rows here correspond to different patients. Columns correspond to different visits. And the third axis correspond to different therapies. So say there's some patient Alice. The first point here would be Alice's ADAS-COG score on visit T under no intervention. The second point would be Alice's ADAS-COG score on visit T under therapy 1, and so on and so forth. Right? If you had access to this entire tensor of potential outcomes, you'd be done. Right? You could answer the question of what would happen to each patient under each therapy. But that's not how your data actually looks like. This is the data we actually had from the company. Okay, so there was a 6-month period before the RC began, where they're collecting baseline information about each of these patients. So that's the first 6 months. So there we actually had data of all the patients under no intervention. But as a result, we had no data of any of their outcomes under therapy 1, 2, or 3. Right? That's the part in white that's missing. And once the RC began, for example, the patients who got therapy 3, we observe them under therapy 3, but we don't observe them under no intervention, therapy 1 and therapy 2. Right? And this really encodes the fundamental challenge of causal inference, is that you only observe one outcome, but you want to know all potential outcomes. So given this kind of sparsity pattern, what does an RCT estimate? At least the naive estimator from an RCT. It tells you the average treatment effect, right? It looks at the average outcomes of everyone who got therapy 1 minus the average outcome of everyone who got no therapy or no intervention, right? is why are they so beloved, RCTs? Why are they used all over clinical trials? It's because there's explicit randomization, right? So there's no unmeasured confounding. But what can RCT not estimate? It can't estimate, for example, the individual treatment effect. For example, what happens to Alice under therapy 1 minus Alice under no intervention? Why? Because obviously you can only observe Alice under one intervention. Right? So this is kind of the limitation of RCTs, is that what might work best on average may not work best for each individual. Right? So there's randomization, but there's no personalization. So let's go back to the question of estimating the ADAS-COG score for each patient under each therapy. Let me show you that this is simply a question of tensor completion. Why? For example, say ask the what if question. What if the no intervention subjects received therapy 2? That really amounts to the shaded green part of the tensor on the right-hand side. That's all it is. Right? There's no coincidence in so elegantly encode this problem through tensor completion. For those of you who are in the causal inference literature, we all say that, well, causal inference is the missing data problem. And for those of us who come from ML, say, well, tensor completion is a missing data problem. So they're really asking the same questions, just with a different language. For example, the notion of different experimental or observational studies that really amounts to different sparsity patterns in the induced tensor. The goal of causal inference, which is estimating counterfactual potential outcomes, that really amounts to imputing specific missing entries in this induced tensor. And this problem that pervades or plagues causal inference of confounding, you can really encode that as this missing not at random data. And I'll make this formal as we go along. Okay? But the key conceptual contribution is that you can encode a lot of interesting problems in causal inference as one of tensor completion. Okay, so this is the question. This is the tensor completion perspective in it, where you're trying to fill out the right-hand side of this tensor, the shaded part here. Right, I'm going to show you now one algorithm to do that called synthetic interventions. So suppose the two people, Bob and Alice. Okay, suppose Bob received therapy 1 after the RCT began and was under no intervention prior. And suppose there's Alice, who continued to remain under no intervention once the RCT began. So what are the counterfactual questions of interest? For Bob, I'd like to know, what if Bob remained under no intervention or instead received therapy 2 or 3? And the what if questions of interest for Alice is, what if Alice received therapy 1, 2, or 3? Okay. So let's focus on one of these questions, which is what if Bob remained under no intervention? One of these 6 questions. That question has been tackled by synthetic controls. I think Avi gave a wonderful introduction yesterday, so I'll be a bit quick. So suppose I want to ask the question of what if Bob remained in no intervention? What you do is look at the pre-intervention outcomes of all the patients who will continue to be in no intervention once the RCT begins. Okay, I'm going to call that matrix of outcomes Y donors pre. I'm going to call the vector of outcomes for Bob Y pre. What you do, or what Abadie and his co-authors propose, is that you write Y pre as a convex combination of Y donors pre. And the second step, you look at the post-intervention outcomes of the units that remain under control, call it Y donors post. You apply the beta hat that you got to get a synthetic trajectory of Bob. Okay, so it's just a beautiful, simple 2-step algorithm. You can repeat this process and fill out the first slice of this tensor. Right? For every patient who got treated, I can come up with the counterfactual, what would have happened to them had they remained untreated. But what synthetic controls can't answer for you is, for example, what if Alice got therapy? So all the parts of this tensor that have a question mark on top of it, that cannot be answered by synthetic controls. Indeed, Abadie himself says in his 2020 review paper in JEL, he says results in estimation with multiple, that is in the presence of intervention, are absent in the literature. Right? And why is this problem not symmetric, synthetic interventions to synthetic controls? It's an asymmetry in data availability. Right? In the pre-intervention period, we have data available under no intervention. We have no data available under therapy. Right? So that asymmetry in the missingness pattern between the slices of the tensor is what makes this problem harder. So synthetic controls, before I tell you about synthetic interventions, let me tell you a little bit more about synthetic controls. It's actually gotten a lot of popularity within healthcare itself. These notion of synthetic control arms are now being used, for example, by Pfizer, by Merck, by Metadata. Flatiron Health is a company that specializes in building these synthetic control arms for oncology. And the FDA is getting more okay with using these kinds of techniques because keeping people on placebo is essentially a death warrant for them. Right? The FDA is more open to statistical techniques. But what it can't answer, for example, is what if Alice got therapy 1, 2, or 3, which is necessary for the Taux case study. And synthetic controls didn't really start from healthcare, start from policymaking and policy evaluation, which is still probably the place it's most popular. And there's a variety of really interesting things that have come out, policy questions that have been analyzed using that, for example, tax legislation, police reform, even Brexit. And I'm going to repeat the same thing Avi said yesterday of what A.T. Nimmin said, which is one of the most important innovations in the policy evaluation literature in the last 15 years. And I must say, I agree. You know, Alberto is my advisor, and I found this framework of synthetic controls to be just absolutely beautiful. And I've dedicated many years of my life to thinking about it because I just think of it as such a flexible and elegant framework to think about so many problems. But as Alberto says himself, is that the results in estimation with multiple interventions are absent, right? So what I hope to convince you through this slide is that there's significant impact of estimating counterfactuals in the presence of interventions. So, okay, so now I'm going to tell you the answer of how would you estimate what happens to Alice under therapy 1. Actually, once you look at it from this tensor perspective, the answer kind of pops out quite easily. What you do is you look at all the patients who are going to get therapy 1, you look at their pre-intervention outcomes. It's called that Y donors pre. You look at the pre-intervention outcomes of Alice, it's called a Y pre. Now you build a linear model between Y pre and Y donors pre. But the way you do this is through a regularized linear regression called principal component regression, which is where you first do PCA and Y donors pre. And then once you take that model learned, beta hat, you apply that to the post-intervention outcomes of the units under therapy 1. Okay. Now you actually look at the post-RCT data. You apply the beta hat to get a synthetic trajectory of Alice under therapy 1. I note here we're using nothing but the ADAS-COG score, because that's all we had access to. Right? No additional covariates have been used. Suppose I want to know what happens to Alice under therapy 2. You do is the same thing, except now you change the donor group. Now you regress it based on the outcomes of the patients who are going to receive therapy 2. You can repeat this process. For example, what happens to Alice in therapy 3? Look at the pre-intervention outcomes of the people who got therapy 3, and so on and so forth. So given this, you can fill out the entire right-hand side of this tensor, right? By iterating between every patient and treatment. And note that no additional data over the additional RCT is being used. No additional experiment is being run. Okay, so just so that we're on the same page, what are some of the key differences between synthetic controls as it stands and synthetic interventions? The first one, probably the most interesting one, is where the model is applied. In synthetic controls, you learn a model under control, and you make predictions under control. In synthetic interventions, you learn a model under control, but you make predictions under intervention. This begs the question of when can a linear model be transferred across interventions? I believe this might have some interesting applications for things such as transfer learning, learning of distribution shift, causal transportability, what have you. And these are aspects I'm very excited to explore. So happy to chat with anyone if they want to. And the second key difference is how the model is learned. What's the statistical procedure? So classically, at least, we use convex regression. But despite that synthetic controls has gotten a whole life of its own in the last 5 years and it's being used everywhere, the theoretical basis of it is catching up in some sense. So lots of interesting questions that needed to be answered. For example, why a convex model? When is that motivated? What's the causal framework? Finite sample guarantees, valid confidence intervals. There's been a lot of work in the last 15 years, or sorry, last 5 years, trying to tackle this question. Work that's being done here at Berkeley, for example, but Avi and his collaborators, with A.T. and Imbens and Wager and their collaborators at Stanford, Abadie and Chernozukov at MIT, and so on and so forth. Right? So there's really been a flurry of activity. And at least for the framework that we propose and the type of causal parameters that we're interested in, it turns out that PCR is crucial to proving our formal statistical guarantees. We'll talk about why. So before I go to the theory, let me show you a validation exercise we ran with the data. So there were 976 patients of data we held out. So for example, in people who got therapy 1, there were 159 of those patients. We held out the data of 109 of them. That is, we held out their data once the RCT began and only looked at their pre-RCT baseline data. Okay? And the question was, could we recreate the outcomes in the post-intervention period using only the pre-intervention outcomes? So in blue here is a true distribution of these patients. What I'm plotting here is a change in the ADAS-COG score pre versus post-RCT. That's what the FDA cares about. And what you want is the yellow is what is being produced by synthetic interventions. So what you want is the blue and the yellow to be on top of each other. At least that's visually what you're seeing. I'll quantify that in a second. Repeated this process with therapy 2 and therapy 3, where there we held out the data of 124 patients and 743 patients. And again, you can see the blue and yellow are relatively close to each other. To quantify this, one way you can do that is through the Jensen-Shannon metric, which is a way of defining the distances between distributions. The closer it is to 0, the better. So 0 means you could perfectly recreate it. 1 means you're maximally different. So at least you can see that the answers are, the difference is close to 0 as you'd hope. A natural baseline to compare with is what would the distribution look like if you use the 50 patients? Okay? You can see it's significantly worse. right? So there is a lot of information gained by using synthetic interventions over this natural baseline. The way we actually created these distributions is by predicting the individual trajectories of each patient. So here I'm just doing a simple validation exercise where we randomly took data of 3 patients from 3 different therapies. So in therapy 1, patient X, so blue is the true ADAS-COG score, yellow is what we predicted, and then the shaded part is the confidence interval that we produced. I'll tell you how we did that. We repeat the process for therapies 2 and 3. Yeah.
Oh, is this like, so this, when I'm looking at the densities that we have here, this is like somehow in aggregate. This is not saying that I predicted you well. It's saying I predicted this aggregate, the
distribution well.
Density well. Not even like the L2 norm, but it's a different kind of thing. Is that right, or is that not?
So you're totally right. The other natural thing to plot, for example, is the average mean squared error or the median mean squared error, and it's also very small. This one I showed it because this is what they actually care about in terms of this is what convinced them that something good was happening. So that's why I showed it. Yeah.
Awesome.
Also, it's visually a bit prettier.
It is.
Yeah.
So the randomization itself, shouldn't that equalize those distributions?
Why would it?
Because it randomized, so that means that the distribution of the potential outcomes in each of the treatment groups would be identical. So the marginal distribution in each of those treatment groups would be the same as the marginal distribution in the other, or the same potential outcome.
But they're going through different therapies, right? So their outcomes will change because of the therapy, because of the intervention.
The observed outcomes will be different. Potential outcomes, the same potential outcomes in the different treatment groups will be the same.
Yes, agreed. Yes, yes. Let me come back to the question in a second. And so this is some current work we're doing with the company. So what did we actually find with that? What we found is that 20% of the patients are actually potentially responsive. If you look at the synthetic trajectory of them under therapy 1 minus a placebo, there was a significant gap. And now what we're doing is looking for predictive biomarkers. So how do you go from these potential outcomes to a detailed causal mechanism? Say, for example, a mechanism from the genetics to these potential outcomes. And that's how to do that in a principled way is something I'm very interested in working on. Maybe people here would have expertise on that. And I think the reason that this company has been very excited is that we can potentially save millions of dollars and also unnecessary human testing. And we've jointly filed a patent with them. And again, I note that we've used no additional experiments to run this, only data from the original RCT. Yeah.
Just a question of 20%. Is that accounting for multiple testing, or is it just individually just keep seeing which one is significant and just found that?
Yeah, all we did here is a simple thing where I looked at the trajectory of each patient. I looked at their synthetic trajectory. I looked at their synthetic trajectory in therapy 1 minus placebo set. And if the gap between the two confidence intervals was large enough, was like bigger than 20, that's all they care about. So I said that was potentially responsive.
I see. And how many patients are in the therapy?
There were 1,162.
And you're defining statistical significance in 0.05 or?
Exactly. Yes. Yeah. And I won't have time to get into this, but we've used this across a variety of other applications. So we've been currently consulting with Uber, done some work on COVID-19, with the Poverty Action Lab at MIT. I don't have time to get into it, but the point is that all of these questions, we could pose them as one of a tensor completion. And they kind of impose different kinds of sparsity patterns in the induced tensor once you model it correctly. And what synthetic interventions does is just help you impute it. That's it. So now we'll kind of get into the theory, which is when and why do synthetic interventions work? What's the causal framework? And what kind of statistical guarantees can you produce? So the two essential questions to me are, one, when can a linear model be transferred between different interventions? And the second one is what kind of confounding is allowed in the observational setting? The first assumption is what I call a tensor factor model. So in general, in synthetic controls, the general framework you require, the general structure you require is that matrix, that first slice of that tensor, the no interventions, is low rank. And this is the low dimensional unit factor and a low dimensional latent time factor that give you that matrix. That's really what lets you share information across units in time. But now if you want to share information across interventions as well, then you need that tensor to be low rank. So here R refers to the CP rank of this tensor, so the canonical polydesic rank. Okay, so now you have a latent factorization across interventions as well. This is what we require on the expected potential outcomes. We model the actual potential outcomes as random. So the epsilon NTD is a mean zero sub Gaussian that models the randomness in the potential outcome. And these latent factors, for example, just to give some intuition, could be, for example, patient genetics, how the ADAS-COG score progresses over T weeks, the chemical pathway used, etc. And this might genuinely be latent, may not be observable through any observed outcome. The second assumption we make is linear span inclusion. So suppose I want to produce counterfactuals for unit n under intervention D. What it requires is the latent unit factor for unit n lies in the linear span of the latent factors for units of the units that got intervention D. Okay. And if you sample the latent factors independently, you can actually show this holds with high probability. And so what do these two assumptions buy you of the tensor factor model and the linear span inclusion? What they buy you is that this implies there exists an invariant linear model that holds across time and interventions. Okay, so this is really what motivates, these two assumptions is really what motivates learning a linear model and transferring it. The third assumption is about what kind of confounding is allowed in the observational setting. So observational data can be confounded. What that means is potential outcomes are not independent of treatment assignment, which is being denoted by script A here. Right? In an RCT, by design, we have potential outcomes independent of treatment assignment. What does that mean in the language of tensors? So the sparsity pattern is induced by the treatment assignment. Right? That is not independent of the entries of the tensor, which are the potential outcomes. That's what I mean by missing not at random. Versus in an RCT, the sparsity pattern is independent of the entries of the tensor. So the question is, what kind of confounding is allowed in synthetic interventions? Under what conditions are your potential outcomes independent of treatment assignment? The type of assumption you require is called selection and latent factors. So the latent factors here are the collection of latent factors per unit, time, and intervention. That's being given by script LF. Conditional on them, the potential outcomes and treatment assignments become independent. So this could be thought of as maybe analogous to the classic selection of observables, where now on the right-hand side would be observed covariates rather than latent factors. And this is the type of assumption that's also been made earlier to us by Athey et al. In their 2018 paper and by Callis et al., I believe, in the 2019 paper. So another way of interpreting is that the latent factors define the expected potential outcomes. So your treatment assignment can only be a function of expected potential outcomes, not observed outcomes. So this would allow for example, adaptive treatment assignment. So if you looked at previous outcomes, saw them, and then decided treatment assignment, this identification argument would break down. And here's a graphical way of looking at it. Here, the LF are your latent factors. They point to both the treatment assignment and the potential outcomes. In that sense, the latent factors can be unmeasured confounders. But conditional on them, the epsilons don't have a direct arrow to the assignments. Okay, so that's the exogeneity you need. The fourth assumption is not really required for identification, but it's needed for statistical estimation, the subspace inclusion. That is, the column span of the expected pre-intervention matrix needs to contain the column span of the expected post-intervention matrix. And this is really a purely linear algebraic condition for generalization. We're not assuming, for example, that your data is sampled IID, because that wouldn't really make sense because the data you sample under one intervention is clearly going to come from a different distribution from a different intervention. What you really require is that your pre-intervention outcomes are sufficiently rich. What that means is the column span is large enough to learn something there. And this, I believe, has some interesting applications to, for example, transfer learning, distribution, free learning, etc. And given how important it is, we provide a formal hypothesis test to check for this. Okay, so putting it all together, when the synthetic interventions work, we did a bunch of hard work, it's these four assumptions. Okay, the low rank tensor factor model, the linear span inclusion, selection latent factors, and subspace inclusion. The low rank tensor factor model you can test for by plotting matrices that are induced by your tensor. And if it is high rank, and if you look at its SVD, then you should not be using synthetic interventions. It's at least a diagnostic when not to use it. The linear span inclusion, you can look at the pre-treatment fit. So we can hold out a little bit of the pre-treatment data and see how well you can fit it. If it doesn't fit well, that means linear span inclusion is not holding. So then don't use it. Subspace inclusion, we provide a formal hypothesis test. The selection latent factors is a somewhat philosophical point. It holds for free, obviously, in RCT. I think what it really precludes you from is adaptive assignment of treatment. That's really when it breaks down. So what kind of theoretical results can you show under these four assumptions? The first is parameter estimation. That is, the beta hat you learn from PCR consistently estimates beta star that's induced by the second assumption. In the high dimensional case, there can be many beta stars that are observation equivalent. What PCR is picking out is the minimum 2 norm 1, which is unique. In that sense, PCR implicitly regularizes. Here R refers to the rank of the expected pre-intervention matrix. P naught is the number of pre-intervention periods, and ND is the number of units that got assigned in dimension D. The second you can show is finite sample consistency. That is the counterfactual trajectory that's predicted by synthetic interventions that consistently estimates the expected counterfactual trajectory for a given unit in intervention. And here T1 is the number of post-intervention periods. And thirdly, if you assume additional assumptions on the scaling of T0, T1, and D, you can prove that your estimate is asymptotically normally distributed around the expected counterfactual outcome.
Estimation procedure, you assume anything about the tensor rank?
The tensor rank of the factor model really shows up in terms of making the linear span inclusion and the selection latent factors more believable. If that's low rank, then these two assumptions are more likely to hold. But the rank of the tensor doesn't directly show up in the bounds. It only shows up in terms of the rank of the pre-intervention donor matrix, which is bounded by the tensor ranks, obviously.
But the rank is fixed.
The rank, what do you mean by fixed?
It doesn't change with your sample size in the pre or the post-intervention period.
We explicitly give the bound in terms of R, right? So it can scale in some sense. Like if this, as long as the numerator is a lot smaller than the work, it's allowed to grow in that sense. Yeah. And so just to interpret, that's a lot of math I've thrown at you. What does that really mean? So what it means to me at least is that if you have n patients in D therapies, I want to estimate those outcomes of all n patients under all D therapies to accuracy within delta. Say hypothetically, you could create D twins of each patient. The number of samples you would need to be able to do that is n times D times 1 over delta square. With synthetic interventions, under those four assumptions, what you get is n times 1 over delta to the 4. Okay? So crucially, you've lost the dependence on D, which is great because especially as you move towards, say, personalized therapies, D is going to start growing. What you've lost, though, is your dependence on delta is suboptimal now. So an interesting open question is, what's the best achievable sample complexity for these kinds of sparsity patterns in the tensor? I believe a natural lower bound is n times 1 over delta square. The question is, can we come up with an algorithm and or an analysis that hits that? Okay, I'm going to end in another minute. I'm just going to spend a little bit of time telling you about principal component regression. That's the key to our entire procedure. So again, what is PCR? Is where you first do PC on Y donor spree to find a low rank approximation before doing ordinary least squares. So why PCR? One, it has a bunch of implicit benefits. The first is that it enforces spectral sparsity in your Y donor spree. And in the high dimensional setting, where the number of measurements might be a lot larger than the number of features, might be a lot smaller than the number of features, this helps. The second one is that it implicitly denoises Y donor spree. Okay, so this helps you deal with the problem of error in variables, which is the challenging problem in statistics, where you can think of Y donor spree as a noisy observation of the expected Y donor spree matrix, which is what you'd actually like to regress against. And I just note that error in variables has many interesting applications. Measurement error is classical in stats, but also, for example, differential privacy, where you actually artificially inject noise into your system, like Laplacian noise, to make it differentially private. You can pose that as a problem of error in variables regression. So the key assumption we make is that the expected pre-intervention matrix is approximately low rank. What we do not assume, though, is a restricted eigenvalue condition on the pre-intervention expected matrix, which is required for, say, lasso-based approaches to high-dimensional regression. And the key intuition, geometrically, what's happening is that your low-rank signal is spectrally concentrated, versus by random matrix theory, we know that noise is spectrally diffuse. And that is really what PCR is exploiting for these low-rank factor models. So what we do is improve the finite sample consistency of PCR for parameter estimation and test error. And this is the first test error result for error in variables regression, plus in a high-dimensional fixed design setting. And this is really crucial for us to prove statistical guarantees for synthetic interventions and to formally analyze synthetic controls itself. And with that, I'd like to, so maybe I'll just give a quick summary, is that what we did is we addressed the unresolved problem of counterfactuals in the presence of interventions, and this provided novel results for synthetic controls. And this is being currently used at Therapeutics and Uber to guide their decision-making. And in doing so, we had to deal with the problem of error in variables regression, and we found that PCR is the right algorithm to do so. We provide the first generalization error result for error in variables regression. Right, thank you very much.
Due to time limit, we will save all the questions to the panel discussion. And our next speaker is Emma Perkovic from University of Washington.